Hello, I'm Adam Rivkin, and I'm presenting my work with David Cash and Ruth titled Improved Structured Encryption for SQL Databases via Hybrid Indexing. We're concerned with outsourced databases. Currently, many modern database applications require massive amounts of data that exceed in-house data storage capabilities. To resolve this issue, applications frequently turn to outsourced cloud servers to store their data from query processing. Services like Google Cloud and Amazon RDS provide accessible cloud storage solutions. However, many applications may also want to avoid storing unencrypted data on third-party servers. If data is stored in the clear, they are vulnerable to theft by criminals and exposure to massive data breaches. Also, applications may be concerned with threat of data abuse. If a third-party server admin proves untrustworthy, they could use their access to snoop on sensitive data. Also, giving server access could violate the confidentiality policies of certain applications, like medical data, where data legally cannot be shared. Therefore, methods which offer protection from these threats, by allowing cloud storage and querying to run over encrypted data, are highly desired. We considered the setting of encrypted databases, where a client wishes to securely outsource sensitive data for storage, and then perform queries over that data. More specifically, we aim to allow the client to perform a meaningful subset of SQL operations on an outsourced relational database. Our threat model is an honest but curious adversary sitting on the third-party server, meaning that the data and queries must be end-to-end encrypted to ensure that the server never sees the information. Take the informal example of a simple SQL selection query on the slide. No encryption is used, so the database contents, the query, and the query results are all leaked to the adversary. The purpose of an encrypted database is to prevent as much of this information as possible from leaking. Our work made progress in this direction by exploring and improving security efficiency trade-offs in the SQL join operation on encrypted data. For those unfamiliar with relational databases, we treat a database as a collection of relations which can be accessed by unique identifier names. Each relation has an n tuple of attributes and a table containing a set of n tuples of rows, where each tuple represents a row in the table. The attributes are used to index values in each row. For example, take a database with two relations identified as table 1 and table 2, which we'll use as a writing example. Both relations have 3 attributes, which correspond to the column names of the relations. And both tables have 5 rows, where the data in each cell corresponds to the value for the row added attribute. Also, rows are required to have a key attribute, which uniquely identifies them within a table. In the example, the first columns of the tables, number 1 and number 2, serve as identifying keys. We call requests to retrieve data from the database queries, and define specific query types later in this talk. Also, for the entirety of this talk, we will only consider static databases, which cannot be changed after setup time. Many different approaches to encrypted SQL can be categorized as either heavy cryptography, using primitives such as fully homomorphic encryption, garbled circuits, and ORAM, or as relying on property-revealing encryption, such as deterministic or order-revealing encryption. These schemes allow a large class of SQL queries to be run, but frequently suffer from trade-offs between efficiency and information leakage. Heavy cryptography schemes achieve the best possible security. There's slow runtimes at large scales, despite our practical implementations. While property-revealing encryption allows fast constructions, they've been shown to be vulnerable to a slew of leakage-based attacks, which render them to have little to no privacy in many practical settings. To give a concrete example of how leaked information can allow an attack, consider the deterministic encryption of a single column of values. If an adversary has access to auxiliary information about the column's data distribution, such as an approximate histogram of the domain, they can possibly infer which domain values correspond to which deterministically encrypted ciphertexts. This was done with high probability on holistic datasets by Naveed, Kumar, and Wright in 2015. A third type of approach is to use structured encryption to build support for SQL. Structured encryption provides a framework for generic data structures to be queried efficiently with relaxed security goals, which can be proven to only leak a well-defined range of information depending on the data and the application. This strikes a middle ground between heavy cryptography, which is secure but inefficient, and property-revealing approaches, which are efficient but insecure. Recent work by Kumar and Meritas and a follow-up with Zadanek and Jail done schemes called SPX and OPX, which use structured encryption to build support for a meaningful class of SQL queries which resisted leakage abuse attacks. While we'll give definitions and explore these topics in more detail later, At a high level, the core idea behind using structured encryption supports SQL. This is using encryption for the multi-map and dictionary data types to build indexes which support certain types of queries. While these schemes can be defined to have provable security, which exclude existing leakage-based attacks. However, we still lack a rigorous understanding of the security efficiency trade-offs in the approaches to supporting encrypted SQL. We approach this problem by focusing on indexing the SQL join operation. Our main contributions are as follows. We introduce a new indexing scheme to compute the join operation. We consider the case where the client has a key and the server has the encrypted tables and index used to compute the join operation over the encrypted data. The client sends a token to the server, which uses the join index to compute the encrypted result. The result is sent back to the client, and the key is used to decrypt the table. Our new index is linear in the database size, in terms of number of rows, which is linear in the size of the join tables, leading to less storage and bandwidth than prior work. Also, the index leaks less to the adversary on the server, so it is more secure. We achieve this by storing only partial information on the server, and finalizing the computation during post-processing at a logarithmic computation cost. Also, we introduce hybrid indexing to handle larger query class and security-aware query planning. For complex queries, our index no longer performs strictly better than the techniques from prior work in terms of storage, in terms of bandwidth, although it is still more secure. To resolve this security efficiency trade-off, we developed a hybrid indexing scheme so lets the client choose between our new indexing technique and the old technique at query time. The server stores two indexes, one for the new technique and one for the old. Then the client can send the token for the first index or for the second. The join technique can be used when encrypted results are returned and decrypted. To help the client decide which index to use to optimally balance performance with leakage in their database, we develop a heuristic query planner to optimize security while maintaining an efficiency threshold. Lastly, we explore the remaining data-dependent factors in our scheme, which can't be resolved with theory alone, running simulations using realistic data of what might be stored in an encrypted database. Here's a roadmap for the remainder of the talk. I'll begin by giving preliminary definitions of structured encryption, the SQL operations we will support. I will present a toy indexing scheme which only supports the join operation, highlight a new technique for joins. Afterwards, I will discuss our hybrid index, which allows client choice to support a more realistic class of queries, and our query planning heuristic, which allows the client to make choices effectively. Lastly, I will discuss the setup and results of our simulations. Structured encryption was developed by Chase and Kamara to model interactions encrypting some data type through a standardized API. The data type is defined by data structure, a set of queries, and evaluation function, each query on the data structure. In our setting, the client starts with the data structure belonging to some data type. At setup, they generate a key from the key set and use an encryption algorithm to create an encrypted data structure, which is sent to the server and stored. At query time, the client runs a tokenization algorithm with the key to encrypt a query queue into a token, which is sent to the server. The server runs an evaluation algorithm on the token and the encrypted data structure to return a ciphertext. The ciphertext is sent back to the client where it is encrypted with the key, where it is decrypted with the key. A key advantage of using structured encryption is that the setup and query evaluation can be provably shown to leak only a vigorously defined amount of information to the server. We now introduce the semantic security of an ST scheme. The security is defined with respect to an adversary, a leakage function, and a simulator. We'll consider non-adaptive security, where the adversary is allowed to use the data structure queries at the start. The leakage function takes that choice and outputs a leakage string, which is sent to the simulator, which constructs the encrypted data structure and the query tokens. We see that an ST scheme is secure with respect to leakage function. There exists a simulator, such that for our adversaries, the ideal world where the simulator is indistinguishable from the real world, with the scheme's encryption, tokenization, and decryption algorithms are used. If no adversary can distinguish between the simulated world and the real world, no information can be leaked beyond what is included in the leakage function. The adversary's goal is to guess which of the two worlds it is in. We define the semantic security of an adversary against an ST scheme with a leakage profile and a simulator as the difference between the probability the adversary outputs 1 in the real world versus the probability it outputs 1 in the real world. A secure STE scheme can still be vulnerable if its leakage function is too large and allows effective leakage abuse attacks. However, designing a scheme with low leakage can prove to be restrictive. We introduced two data types which will be relevant later. The dictionary is data structure mapping a label to a single value. For example, the dictionary in the slide maps integers to strings. A multi-map maps a label to a set of values. For example, the multi-map in the slide maps strings to sets of integers. Starting the study of searchable symmetric encryption, STE schemes for the dictionary and multi-map data types have been studied by prior work. Current schemes are secure, leaking only some metadata, the number of labels in the data structure, and query-dependent information, like if the same query has been issued multiple times. Also, they can be built efficiently from the simple application of commonly deployed cryptographic techniques like symmetric encryption and pseudo-random functions. At a high level, they work by encrypting the table with standard encryption and using a pseudo-random function to derive keys to partially decrypt information when needed, which can be sent as tokens. Rather than handle the details of specific STE constructions, we'll treat dictionary and multi-map encryption as subprotocol access to the STE API for the remainder of this talk. We will use these STE schemes as building blocks within the new STE schemes we develop for the SQL data type. We'll now define the two SQL operations we will use for the remainder of the talk: selection and the join operation. Well, these are only two operations. They were shown by Chandra and Merlin to capture the class of conjunctive queries, a large and useful subset of SQL, if we allow projections to be treated as post-processing. We define a selection operation to take an attribute and a value that filter relation to only include the rows where the cell corresponding to the attribute in each row is equal to the specified value. We use the standard notation of writing sigma for selection. Consider the example of selecting all rows from table 1 where the attribute goods1 is equal to the string gold. 3 rows match that predicate and are returned in the resulting relation. Rows B and C have the value pets in vans, so they are excluded from the selection. We define equijoins as an infix operation between two relations. Equijoin, which we will call joins for the remainder of this talk, takes two equal length tuples of attributes and merges the two relations into one by concatenating their sets of attributes and returning the union or cross products of each set of rows which have equal values add those attributes in each relation. Consider the example where table 1 and table 2 are joined in the single attribute tuples goods1 and goods2. Rows B and alpha have an equal value of pets, so one new row is included as the cross between those two rows. Then 3 rows from table 1 and 2 rows from table 2 have the value gold, so the cross between those two sets adds 6 more rows to the resulting table. The remaining rows from the two tables have no rows in the opposite table with an equal value of the corresponding attributes, so they have no matches and are excluded from the join. Next, we will build an example construction to support a subset of SQL which only allows single attribute joins. We define a simple query class to highlight a new indexing technique. We introduce the join data type, which includes only single attribute joins. Queries of the form relation identifier 1 join relation identifier 2, and attribute 1 equals attribute 2. In realistic databases, not all attributes can be logically joined. To reflect this limitation by specifying in advance the pairs of attributes which we will allow to be joined. At a high level, to support this class with structured indexing, we pre-compute all such allowed joins and then index the results. The first method to achieve join operations is fully pre-computed or FP indexes as done in SPX and OPX. In order for the server to complete a join, it must know which pairs have equal values at the given attributes. Take the example of joining table 1 and 2 on goods 1 and 2 from earlier. Row A from table 1 has the same value of gold as rows beta and gamma, so the pairs A beta and A gamma must be stored. Similarly, row B and alpha have the same value of pets, so the pair B alpha is needed. There are no matches for row C and 2 each for D and E. Pre-computing and storing the pairings of rows, visually represented by the arrows in the slide, allows the join to be computed even after the tables have been encrypted. To store this indexing information in encrypted data structure, we use a multi-map. For each joinable pair of attributes, we pre-compute and store the pairs of rows which are equal to that attribute, and therefore correspond to a new row that joins resulting relation. We will use the multi-map data types encryption function to encrypt the index and store it securely in the server. Continuing with our example, the goods 1 and 2 attributes can be joined, so the pairs of rows are stored under those attributes in the multi-map. When the multi-map is encrypted and then evaluated, the results will give pointers to the rows of the encrypted data that can be accessed to return the necessary ciphertext. Let's consider the leakage and bandwidth of FP indexing. The client issues a join query. The server sees which pairs of rows will be joined, even when the rows are encrypted. These pairs allow an adversary sitting on the server to discover the equality pattern of the access to rows. Take the example on the slide. Say that the client sends a token to the server, the encrypted index is searched to reveal the pairings between row numbers. The adversary knows that the rows will be paired if and only if they're equal to the specified attributes, so they know that all rows connected by arrows in the visual will be equal. An adversary watching the server can now use the type of leakage abuse attack described earlier against deterministic encryption. The adversaries access a histogram of approximate domain frequencies and use them to infer plain text values. Also, we can consider the bandwidth and storage of FP indexing. In the worst case, all rows in both joined tables could be equal, resulting in a quadratic number of pairings. In this case, the quadratic number of rows must be transported back to this client, which may be costly bandwidth. A quadratic number of values must be stored in the multi-map. Next, I will introduce our new method to achieve join indexing, the partial pre-computed or PP indexes. Instead of completing the join server, we store which rows are needed for the client to complete the join. Let us use the same example of the join as before. Row A is needed for the join, so it will pair with some row in table 2. Row B is needed for similar reasons. Row C is not needed because it has no pairs, but rows D and E have pairs and therefore will be required. The same process can be done for table 2, so that the rows alpha, beta, and gamma have some pair in table 1, the rows delta and epsilon do not. The arrows now show which rows are necessary client side for the join to be completed, not the exact rows they will match with. To store this information index, we'll use 2 multi-map labels for each join. The first label references the row number from relation 1, accessed for the join as values. The second label references the row numbers from relation 2. Tokenization sends tokens for both labels, and evaluations using the resulting pointers retrieve only the rows needed to complete the join. When these rows reach the client, the join is computed during post-processing. Now we'll consider the leakage, bandwidth, and post-processing cost of partially pre-computed joins. The server now sees only which rows from each table have some row in the other table that matches. An adversary sitting on the server can use that leakage to tell that each row in the join equals at least one row from the opposite table at that attribute, and does not equal rows not involved in the join. However, this information is not enough to allow existing leakage abuse attacks from the literature. For bandwidth and storage, in the worst case, partial pre-computation stores and sends at most a number of rows linear in the size of the access tables. Also, we observe that since the client must already traverse the sets of rows in both tables for decryption, the join can be completed by storing the rows as decryption takes place and joining the sorted rows, leading to at most a logarithmic increase in computation time asymptotically. To summarize, full pre-computation leaks the quality pattern of rows, uses quadratic server storage, sends a quadratic bandwidth in the worst case, and decrypts the train relations as post-processing. On the other hand, partial pre-computation leaks which rows are accessed by the join in the partial equality pattern, uses a linear storage, sends a linear bandwidth, must decrypt and spend a logarithmic amount of extra time completing the join during post-processing. For this query class, PP has strictly lower leakage, never has the worst bandwidth, it's a comparable runtime to FP. However, the situation is not as simple once we expand your construction from only joins to support a query class with more realistic usage. Next, we'll show the trade-offs which come with complex queries and present an index which allows the client to choose which technique they want to use. A complex query class spans the join data type by adding support for selections, recursive queries, and multi-attribute joins. For example, consider the query which selects for goods1 equaling pets on the subquery, which returns the relation from joining table 1 and 2 on goods 1 and 2. We can compute the subquery to give the resulting relation from the join as we've seen before, and then apply the selection to filter the rows of the relation down to single row where goods1 equals pets instead of gold. We can support this query class through a straightforward extension of our pre-computation strategy, achieving joins with either full or partial pre-computation, with the one exception that we fold the OXT hash filtering technique into our indexing scheme similarly to OPX. This allows us to reduce leakage on recursive queries. Our new query class introduces new trade-offs between FP and PP indexing strategies. We begin with an important observation that PP indexing now sends unnecessary rows to the client, resulting in the new possibility that PP indexing can send a greater bandwidth of data than FP indexing. The necessary rows can result when a PP join is the subject of another selection of join. Since partial pre-computation does not store the pairings of which rows match between tables, the filtering rate of rows from one table can't be applied across the tables to exclude rows which no longer need to be sent, since their matches have been removed. Take the example of a complex query from the previous slide, joining goods 1 and goods 2, and selecting where goods 1 equals pets. Here with the matching pairs used by FP indexing, they can compute the join subquery as before. The server can apply the selection to filter the pairings where goods 1 does not equal pets. Once these pairings are removed, only a single pair in the join matches the selection criteria. However, when we consider the information stored by the partial index of the subquery, we can see that when the server applies the select to remove rows from goods 1 not equal to pets, it cannot filter out rows from table 2, so it doesn't know which of the matching rows from table 1 have been removed or not. Only the results from table 1 can be filtered down to a single row, whereas all the rows accessed in the join must be sent from table 2. Therefore, PP sends 4 rows as bandwidth, while FP only needs to send 2. There is now a trade-off between the two schemes. PP indexing has lower leakage and storage, however neither scheme has strictly better bandwidth. FP indexing can send more rows than PP by a quadratic factor discussed with the earlier query class, but PP can send almost the entire database unnecessarily in the worst case. But partial pre-computation is still a preferable choice from a security and storage standpoint. It might give too costly bandwidth overhead for practical usage. Therefore, we present a hybrid indexing scheme which allows the client to choose which indexing type they want to use for each join in a query. We first extend our indexing scheme to support both join types, and then allow each join of a query to be annotated as either FP or PP, for the client to specify which type of join they want the server to make. Our scheme allows the same set of queries as before. Now each join can be specified to be computed through either the full or partial pre-computed index. Next, we present a client-side query planner to heuristically choose the optimal hybrid query. Ideally, the client could issue the query with the least leakage, while requiring manual bandwidth of rows to be sent. To approximate this goal with a heuristic, we first let the client specify a bandwidth limit of how many rows they can manage as the maximum bandwidth. Then the client stores statistics which allow them to estimate the bandwidth of a given hybrid query. When the client issues a regular unannotated query, the client takes the query and statistics and uses them to the heuristic optimizer, which produces an annotated query which is sent to the synchronization algorithm. The heuristic optimizer runs by estimating the bandwidth of all possible FP and PP annotations for each join in the query. We note that this is potentially exponential in the number of joins. However, we heuristically assume that for a realistic SQL query, only a small number of joins will be made. The optimizer takes the results of these bandwidth estimations and chooses the annotation with the minimum number of FP joins and an estimated bandwidth below the client specified bandwidth limit. To estimate the bandwidth of an annotated join, we use query planning techniques inspired by those used for server-side bandwidth estimation and unencrypted SQL query planning. The client will store histograms of each attribute's domain and the total size of each relations table on the client side. For selection and joins, the client will assume that the operation is independent from the subquery and apply the frequency from the specified attribute's histogram to estimate the operation on the subquery. We allow the client to choose between 3 options to control the size of the histograms they must store. although we also allow the client to pre-compute and store query sizes in advance, instead of using histograms, which we discuss more in the paper. The options with the greatest storage and highest accuracy is to store full histograms with frequencies for each value in the attributes range. However, for attributes with large ranges, this may be too cumbersome. So we allow the client to store bucket histograms, which group values to a maximum of a specified number of buckets, and then assumes the data are distributed uniformly in those buckets. Lastly, we allow the client to assume uniformity to accommodate clients with very limited storage capacities. Lastly, we will give the setup and results of our simulations. We run our simulations on real-world data taken from MySQL's samples killer benchmark in 15 frequently accessed relations in the City of Chicago's Open Data Portal. We used a total of 30 relations with 175 attributes and 200,000 rows. We simulate the service storage size of our various types of indexes, the query bandwidth of FP versus PP indexing of all possible non-empty single attribute joins in our database, the query bandwidth of FP versus PP indexing on 225 randomly generated complex queries in different formats with 1 to 3 joins and 1 to 2 selects, and the accuracy of our heuristic to use the optimal annotation for these queries. We find that FP service storage is much larger than PP service storage due to the potential for quadratic blowout by several hundred% more value stored. Also, for simple join queries, the FP bandwidth is larger than the PP bandwidth by a factor of 1 to 8,000 times as many rows sent. However, on our complex queries, the story is more complicated. Compared to the ideal situation, only the rows needed to compute the join, client side, are sent. FP sent between 1 to 48 times as large a bandwidth as ideally needed for 3 table joins, and PP sent between 2.4 and 17 times as large a bandwidth for 3 table joins. We note that FP performed better on average for these queries, but worse in the worst case. Lastly, our heuristic consistently gets better results than the baseline accuracy of guessing the random annotation, and gives more accurate results with more storage. For example, we queried with 3 joins and 0 to 2 selects. Our heuristic chose the optimal annotation on an average of 56.4% of the time across all our storage size options, compared to baseline of 12.5% accuracy. Over our 225 simulation queries, our heuristic chose the optimal query 88% of the time with full histograms, 63.6% of the time with bucket histograms, with bucket size of 200, and 33.8% of the time when only assuming uniformity. That's all for the talk. You can see more details in the paper. Thank you for your time.